Okay guys, so we're going to go ahead and start a new topic now. So remember I said that in physics we try to model the world mathematically, and the simplest thing to model is an object moving in a straight line. So we're going to go ahead and start the topic of one-dimensional motion. Objects moving in a straight line. So even though we live in a three-dimensional world, if an object is moving in a straight line, we say that this is one-dimensional motion. So in order to study an object that is moving, we need a reference frame. And the natural reference frame for an object moving in along a one-dimensional line will be the real number line, so the x-axis. So let's suppose that we have a person, and we're going to study their motion as they move along a straight line. So this is our reference point. So all positions will be measured relative to that point. And that is just simply the origin of the coordinate system. It's the origin of the real number line. And the person's starting position, so that is their position at time equals 0 seconds, is called x sub 0, or it's pronounced x naught. Sometimes we also use interchangeably with x naught, we use x sub I standing for initial. So let's suppose that a person starts at time is equal to 0. They start 2 meters to the right of the origin. And let's suppose they move along a straight line. So this is one-dimensional motion. And they move to a different location. So they displace themselves. And at some later time, they're now located at x sub f, f standing for final. So this is their final position. This will be their position after some time t, seconds have elapsed. And let's say they are now 4 meters to the right of that reference point, the origin. So we can now define the change in position, delta x. So remember, capital delta here means change, and x means position. So this is the change in position. There's been some change in position, and we want to quantify it. Now, this change in position has a name in physics. It's called the displacement, and this is a vector quantity. So the way we're going to define this is the final position of the object, which in this case is the person, minus the initial position of the object. So in this particular example, the displacement of the person would be 4 meters, which is their final position, minus their initial position, which is 2 meters, which gives us a positive 2 meter displacement. Now remember that displacement is a vector, so the sign, either plus or minus, of the displacement in one dimension would indicate direction. So the positive sign means that the displacement was to the right. In other words, that means that the person ended up to the right of where they started. Now, suppose we have a situation where a person is moving to the left. Let's say at time is equal to 0, they start at 5 meters, and then after some time has elapsed, they now end up at position x final of 0 meters. So what would the displacement be in this case? Well, that would be position final minus position initial. So our final position is 0, which is the origin, the reference point, minus the initial position, which is 5. So now we have a negative displacement, negative 5 meters. And remember that displacement is a vector, so the sign of the displacement in one dimension is going to indicate direction. So the negative sign means that the displacement was to the left. So the person ended up to the left of where they started. And basically the displacement is really just a measurement of the shortest distance between the person's or the object's starting position and ending position. Now, what happens if the person changes direction? They're still moving in a straight line, but let's suppose they change direction. So let's say they start off at 2 meters, they walk over to 7 meters, but then they turn around and head back and end up at x final equals 5 meters. So what would the displacement be then? Well, remember that the displacement really, or at least its magnitude, represents the shortest distance between the starting point and ending point. So the starting point is right here. This is where the person starts, and this point right here is where the person ends. This other point over here is just some intermediate point, and it doesn't matter as far as displacement is concerned. Displacement, all that matters when calculating displacement is the initial point and the final point. Any intermediate point doesn't matter. So what you can say here is that the change in position is x final minus x initial, and x final is 5 meters minus x initial, which is 2 meters. So you end up with a displacement of positive 3 meters. And the positive, remember, means that the displacement was to the right. So the person ended up to the right of where they started. Now, the 3 meters, if you really think about it, just represents the shortest distance from the starting point to the ending point. So if you ever are wondering what the displacement of an object would be, just think about what the distance is between the starting point and ending point. And then the sign, whether it's positive or negative, just tells you if the person or object ended up to the right of where they started or if they ended up to the left of where they started. So what if the person moves but ends up at the exact same point where they started? So let's say a person moves to the right, then turns back around and ends up exactly where they started. Well, in that case, the final position is exactly equal to the initial position. So this difference is going to vanish. It's going to give you 0. So in the case where the object ends up exactly where they started, the shortest distance between the starting point and ending point is 0. So your displacement would be 0 in that case. But surely the person moved. So we need to define a new quantity that allows us to calculate or quantify the total distance traveled by the person. And this is going to be called the distance. And this is going to be the total length traveled. So let's suppose in the previous example here, let's say the person moved 5 meters to the right and then 5 meters to the left. So they ended up exactly where they started. So remember, the displacement was 0, but the distance d, let's call it, is not 0. So the distance would be the total length traveled. So even when moving to the left, distance would still be positive. So distance is a scalar. It has no direction to it. So moving right, it's positive. Moving left is also positive when it comes to distance as opposed to displacement. So we move 5 meters to the right plus an extra 5 meters to the left for a grand total of 10 meters traveled for the distance. Now, what about if we have a situation like this, where we have a car and it travels 200 meters to the right and it ends up over here, and then it turns around and comes back and ends up over here somewhere after traveling, say, 100 meters to the left. So just to be a little more clear on this, the 200 meters is this distance here. So the car traveled first 200 meters to the right, and then it turned around, it changed direction, and moved 100 meters to the left. So now we moved 100 meters to the left. So what would the displacement be in this case? Well, notice I didn't give you an initial position. But nevertheless, you could calculate the displacement, because remember that the displacement is just the shortest distance between the starting point and ending point. And as you can see, the ending point is to the right of the starting point. So your displacement vector would be a vector to the right. And since that vector is to the right, in one dimension, remember the direction right is going to be assigned a positive sign. And then the shortest distance between the starting point and ending point is going to be 100 meters, which is what this distance is here. This distance would be 100 meters, because it would just be the 200 minus the 100. So this would be the displacement of the car. Now, what about the distance traveled, though? So the distance traveled would be the total distance traveled. So the car has to first travel a distance of 200 meters to the right. And then it turns around and travels 100 meters to the left. So the total length traveled, which is the distance, would be 200 meters. And remember that distance is a scalar, so even though the car is moving to the left eventually, that 100 meters is still positive. Because remember, distance is the total length traveled. So that's going to be 200 plus 100, which gives you a distance of 300 meters. So we could now introduce the idea of average velocity. So let's suppose we have a car, and let's say the reference point is here, and it starts at a position at time is equal to 0. So this is the car at time is equal to 0 seconds. It starts at a position 10 meters to the right of the reference point, the origin. And then time elapses, and as time elapses, the car moves to the right, and at time is equal to 10 seconds, the car is now at x final equals 40 meters. So we can go ahead and calculate the displacement. So the displacement, remember, was x final minus x initial, which will be 40 meters minus 10 meters, which will be 30 meters to the right. So the car displaced itself 30 meters to the right. So that part was easy. So the position of the car changed by 30 meters to the right. But we wanted to find the rate, or to be more specific, the average rate at which the position of the car changes. The average rate at which the position changes. And this is called the average velocity. So the symbol for it is going to be V with a bar over it. The bar just represents average. Sometimes it's also written as VAVG for average. And the way we're going to define this is the amount of displacement that has occurred, which in the case of the cars, the position of the car changed by 30 meters to the right, so its displacement is 30 meters, positive, divided by delta t, and delta t is called the time interval. This is the amount of seconds that it took for the object to displace itself by an amount, delta x. So in our case, our time interval, you can think of the 0 seconds as our time initial. This is our starting time, and then 10 seconds as our time final. That's our ending time. So our time interval, in this case, would be delta t. You can think of that as t final minus t initial, but t initial is usually going to be 0 unless otherwise specified. So delta t is just our time final, which is 10 seconds. So it takes 10 seconds for this car to displace itself to the right by 30 meters, for the car's position to change by 30 meters to the right. So we can now define our average velocity as 30 meters of displacement to the right divided by 10 seconds. So there's 30 meters of displacement, and it took 10 seconds for that displacement to occur. So our average velocity is 3, 30 over 10 is 3, and the units would be meters per second. So on average, this car traveled 3 meters every 1 second for 10 seconds. Now, the reason I say that this is an average velocity is because this is an average taken over a time interval. So the time interval in this case is 10 seconds. And the average velocity is telling me how many meters of displacement occurs every second for 10 seconds. But maybe in the first second, the car displaced itself maybe 4 meters to the right. And in the next second, maybe it only displaced itself, maybe it slowed down a little bit and only displaced itself 2 meters. And then in the third second, maybe it displaced itself 4 meters again. And then it all averages out in the end over the full 10-second time interval to 3 meters per second. So this is the reason why I call it an average velocity, because this is an average taken over a period of time as opposed to the velocity at a particular moment in time. So when you look at your speedometer on the car and it says 50 miles per hour, it is not an average, because that's not your average velocity or average speed over a period of time or over an interval of time. That's your speed at that particular moment in time. And that would be called an instantaneous velocity or instantaneous speed. And that's going to be a topic for another lecture. So in this lecture, I'm only going to introduce the average velocity. There is a distinction to be made between average velocity and average speed. So average speed, unlike average velocity, takes into account the total length traveled or the distance. So the average speed would be the distance traveled divided by the time. So let's suppose that we have a car that travels 500 meters to the right, and then it changes direction and comes back 100 meters. So now it ends up over here somewhere. So if I wanted to calculate the average speed, first of all, I would need to figure out, I would need to be given the time that it takes for the car to travel this distance. So let's suppose that all of this occurs in a time interval, I'll just call that time, of 50 seconds. So 50s. Okay, so the distance traveled is the total length traveled. So 500 meters to the right plus 100 meters to the left. Remember, distance is a scalar, so even though the car was moving to the left, the distance is still positive. So that would give me a total length traveled or total distance traveled of 600 meters. And the time that it took is 50 seconds. So the average speed over this time interval would be 600 meters in 50 seconds, which would give me 12 meters per second. Now remember, this is the average speed, right? This is the average speed. So on average, the car traveled the distance of 12 meters every second. But remember, this is an average over 50 seconds. So maybe in one of those seconds, the car traveled more than 12 meters. And in another one of those seconds, the car traveled less than 12 meters, but it all averages out over that entire 50-second time interval to 12 meters of distance traveled per second or every second. So we can now discuss something that you're going to be seeing in your first virtual lab. We can now discuss the idea of a motion diagram. Okay, so what is a motion diagram? So let's suppose that we have an object, which is a car, let's say. And since all of the particles, all of the points on the car are all doing the same thing, they're all moving to the right at a particular speed. Let's say the car is traveling to the right at 27 meters per second, which is about 60 miles per hour. Every single point on that car is traveling to the right along a straight line at 60 miles per hour or 27 meters per second. So we're going to model that car as a dot. We don't have to keep track of all of the dots, all of the points on the car, because they're all doing the same thing. So we're going to model the car as a point. And indeed, this is going to be true for any object traveling in a straight line. All of the points on the object are all going to be traveling along a straight line at the same speed. So there's no need to keep track of all of those points. We can model the object as a single point. So let's suppose that this is the car at time equals 0 seconds. So after just 1 second, the dot would be at a different location. So at time is equal to 1 second, if the car started at 0 meters, the car would be at 27 meters, right? Because in 1 second, the car, which is represented by the dot, has to move to the right 27 meters. And after just 1 more second, at time is equal to 2 seconds, the car will now be at x equals 54 meters. So it will travel another 27 meters in that 1 second time interval from 1 second to 2 seconds. Now this is assuming something. We're making an assumption here. The assumption is that v, which is 27 meters per second, is a constant. That the car doesn't speed up or slow down. And indeed, this is the first one-dimensional motion problem that we will encounter is an object moving in a straight line traveling at a constant velocity. And then at the next second, at time is equal to 3 seconds, we will be located at x equals 81 meters. And you notice a sequence of dots, and I can go ahead and connect those dots with arrows indicating the direction of motion. And you'll notice that the spacing between those dots is constant, which is a reflection of the fact that the velocity of the car is constant. This diagram, the sequence of dots, is called a motion diagram. And it just represents the motion of an object, which could be a car, it could be a person walking, a person running. It just represents the motion of an object traveling in a straight line. Now, whenever the velocity of an object is constant, the spacing between these dots will stay constant. So if velocity equals a constant, here I'm symbolizing v for velocity, this implies the spacing between dots will stay constant. So this is very, very important. So what we can do now is we could actually make a table. And this is something you're going to be doing in your virtual lab. So my first column is going to be my independent variable, which is time. Time runs independently of anything else. So 0 seconds, 1 second, 2 seconds, 3 seconds. And then my second column is going to be my position, which is in meters. And position is the dependent variable because it depends on the independent variable, which is time. So the position of the car at 0 seconds is 0 meters. The position at 1 second is 27. The position at 2 seconds is 54. The position at 3 seconds is 81. And you'll notice that I have a set of ordered pairs now, right? And those ordered pairs can be plotted. Now remember, the independent variable goes along the horizontal axis, so that will be time. And then the dependent variable goes on the vertical axis, which is position. So I'm going to go ahead and plot those. And if you plot those, this is 0, 1, 2, 3. And this you could say is 27, 54, and then 81. If you go ahead and plot those, you'll end up with a straight line like this. Now this graph here does not represent the trajectory of the particle, right? Because the trajectory of the particle was a straight line to the right. This is just a graphical representation of the position of the object as a function of time. And this graph has a very special name. It is called the position versus time graph. So this is a very important graph that we're going to be studying in the first few chapters, and you need to become acquainted with it. So what would the slope of that line represent physically? So if you remember slope, to calculate it, you need to calculate the rise and the run, right? So the rise, we go from 0 to 81, so that would be 81 meters, right? That's the rise. And then the run, we go from 0 to 3 seconds, right? So if we go from 0 to 3 seconds, the run would be 3. So this run here would be 3. So the slope, which is rise over run, would be 81 meters divided by 3 seconds. Because along the horizontal axis, I have seconds as my unit, because that's time. And if I do that, I end up with 27 meters per second, which happens to be the velocity. So what we just learned is a very important feature of position versus time graphs. That the slope of a position versus time graph represents velocity. And this is such an important feature that this is something you should really highlight in your notes, because we're going to be using this concept throughout the next few weeks. Now, the slope of a line is constant. You can see slope really represents the steepness of the graph, right? But the steepness of this line is the same at every point. So the slope is constant, and since the slope represents velocity, that implies that the velocity is constant, but we already knew that. So, very important, the slope of a position versus time graph is equal to velocity. Or the steepness of a position versus time graph represents velocity. So this is very important. Now, what about the y-intercept? So let's say this is position in meters, and this is time in seconds. What would the y-intercept represent? So let's say this position here is 5 meters, and over here, this is 0 seconds, right? So at 0 seconds, what is our position? Well, we would go to 0 seconds, and then we would go up to the graph, and apparently, the position at 0 seconds is 5 meters. But 5 meters is the y-intercept. So the y-intercept, let me write that a little bit better here. The y-intercept of a position versus time graph is the starting position, or the position at time is equal to 0, which is x naught, or x of 0. Okay, so the position at time is equal to 0, and I'm using here function notation. So this is x, which represents position at 0 seconds. So position is a function of time. So your first virtual lab will make use of all of these concepts that we just learned here. And we're going to explore these concepts a little bit more in the next lecture.